Hello, in this video we're going to be talking about lipids, so it's not wasting your time. Let's get right to it. Now when we're talking lipids, okay, hey, we're talking about fats, fatty acids. We're also talking about non-polar compounds that are hydrophobic. And in essence, that's the same thing. When we talk hydrophobic, we'll dive into that deeper. But it's a reference point that they don't mix with water. They're insoluble in water. In other words, they don't dissolve in water. If fats could dissolve in water, man, that would change the diet industry. Then you could just eat what you want and drink lots of water, and it would dissolve the fats, and then boom, we'd all be as skinny as we wanted to be. But does not dissolve in water. They're not true polymers. The concept of monomers and polymers, they have those concepts. There is a single subunit. They are built into large molecules, but they're not true polymers in the sense that the other three are. Some examples of lipids: fats, as we mentioned, oils, waxes. And not just wax in general, but like the waxy coating on leaves that helps them not to dry out. Those are lipids. The waxes that animals and birds will spread onto their feathers or fur to make the water just drip off. So if you wax your car, you're using a lipid. Cholesterols, hormones, vitamins, those are also examples of lipids. And they're excellent for energy storage. As I mentioned in the initial video, if your molecule has lots of CHs, then they have lots of energy. And lipids have lots and lots and lots of CHs, as you'll see when we look at the structure. Some examples of lipids: estrogen, which we're very familiar with that word. Progesterone, testosterone, again, very familiar with that word. Those are examples of lipids. All right, the idea of hydrophilic and hydrophobic, super important concepts to make sure you master. The suffix is kind of what defines the word: philic, Philadelphia, love. So water, hydro. Love water, hate water. Molecules don't actually hate or love water. That's an emotion that we have. But what it does mean, if you're hydrophilic, that means you'll mix with water. In other words, you can be dissolved in water. If you're hydrophobic, that means you will not mix with water. Okay, you are not dissolvable in water. And there's a reason for that. A polar molecule, as we talked about in chapter 2, bonds with other polar molecules. And since lipids are nonpolar, then they won't bond with water. So it isn't that the molecule is choosing not to or just being stubborn. It simply can't. Water cannot bond to it. So if the molecule is polar or charged, then it's will bond with water. But if it's not charged, it doesn't have a charge, it doesn't have those electrons to one end, closer to one end, then it cannot bond with water. All right, when we're talking fats, we got to talk triglycerides. Now this figure beside me here, it's also in your books and in the PowerPoints, so you can see it there, especially if it needs to be a little bit bigger. But the idea of triglycerides, TRI, prefix, tri, 3, reference to 3. Triglycerides are formed by taking 3 fatty acid tails, and then bonding them to a glycerol backbone. The glycerol backbone is at the top. That you've got your 3 carbons with your OHs all around. In other words, they can anchor they can attach to a lot of other molecules. And of course, your fatty acid tails also, you can see there in the orange circle, have an OH attachment point. And so one of the OHs from the glycerol and the OH from the fatty acid tails will form dehydration synthesis. Another reference to dehydration synthesis. Again, if you're keeping track, we're probably in 100, or not in 100, we're probably we're way up there. And we will continue to be way up there, continue to climb that number. But you can see in the bottom part of that diagram, now you have your glycerol backbone, which is on the far left. It's just stretched out. But you can see your 3 carbons, you can see your 3 oxygens, where dehydration synthesis has occurred. And then you got your 3 fatty acid tails. And those fatty acid tails have some unique characteristics that we'll talk about in the next video. But that's the triglyceride. Glycerol backbone, 3 fatty acid tails that are attached, dehydration synthesis. You got your OH attachment point, your trailer hitches. You've got your bonding elements, oxygen, to form a triglyceride. Okay, phospholipid. Okay, this molecule is super important. I mean, it forms the phospholipids are what form the plasma membrane, which we're going to talk a little bit about in our next slide. But it also has its own chapter, chapter 5, plasma membrane. We'll also talk about it in 4 when we're talking organelles. But again, it's just important to get the structure down of a phospholipid. You can see the phosphate group at the very top, and you can see that little negative beside the oxygen on the far right. That's what makes it, that's what gives it its charge. Okay, and it has that charge as we just talked about in our last slide. If it's a charged molecule, then it can bond with water or attach with water, and that's the phosphate heads are hydrophilic. Okay, and then you've got your glycerol there in the middle, and then you've got your attachment points and your fatty acid tails. So essentially, you've got a diglyceride, 2 fatty acid tails, attached to a phosphate group to form a phospholipid. And again, you can see one of those tails is bent. That is a unsaturated fatty acid tails, and we'll talk about those in the next video, what's going on there and why that's so helpful and healthy for us as well. But that's a phospholipid. Now, as I mentioned, phospholipids are super important because they form the plasma membrane of cells and of particular organelles if they have a membrane. And that, as you can see there in the diagram beside me, get your phospholipid. The head group, hydrophilic, as I mentioned, it will bond with water. It will associate with water. The tails, hydrophobic, they will not bond with water. Now, the important thing to recognize with phospholipids is that because of that charged end and non-charged end, when they are placed into a solution, they will orientate themselves in this manner, with the heads on the outside facing the watery solution, the aqueous solution, and the tails on the inside away from the water or aqueous solution. And they do that because of the charge and the non-charge, which I mentioned, the charge being the head, polar, and the non-charged being the tail. Well, that's our video on lipids, general information, with some looks at some of the unique characteristics. We looked at the structure of a triglyceride, the phospholipid, and established it as the what makes up the membrane. So in our next video, we're going to be talking about unsaturated and saturated fats. So we'll see you then.